Okay, so today we start chapter 4. Today's lesson, I should warn you, is a little bit longer because it will cover actually two sections. Both sections, though, deal with a complete formula for how to solve this particular ODE, namely the second order linear equation, homogeneous with constant coefficients. So we have a complete method of solutions if these conditions are met. Linear ODE, as I mentioned before, most of the course is focused on linear equations or systems of equations. This time, this one is the second order, right? Last time we learned how to solve the first order ODE. This is a second order ODE, homogeneous. There's zero on the right hand side, and constant coefficients. So in this particular case, we're going to require the coefficients to not depend on t, but to be constants. Later on, there will be another lesson on how to deal with the non-homogeneous part of the equation and some practical applications of the second order. The reason I want to spend a little bit more time on this is because I would like to provide some proofs on how the solution is obtained in some cases. Again, you won't need the proofs themselves when you go over solving this equation. You just use the formula sheet, which you should have it in front of you, by the way. When we go over examples, have the formula sheet in front of you. But as I mentioned before, it's very useful to know what's behind these formulas. Whenever with the proof, it doesn't take too long. And in this case, it's not only doesn't take too long, but also it's easy to understand, in my opinion. So you'll see solving this actually requires analyzing three possible cases. And in two cases, like I said, we're going to provide a proof of how the solution is obtained. So let me remind you, though, before we proceed with how to solve this equation, that we showed last time in one of the earlier lessons that any linear homogeneous ODE will have the general solution expressed in terms of a linear combination of independent solutions. For the first order, we need one solution. For the second order, this time, we're going to need two independent solutions. So from that major theorem we discussed earlier, we know for a fact that the general solution of this ODE will certainly look like this, a linear combination of two independent solutions. So that's one of the consequences of that major theorem we talked about before. If this were a third order equation, homogeneous, then the general solution would be a combination of three independent solutions. So we already know we need two independent solutions, y1 and y2, and we already know that my solution will depend on, this time, two arbitrary constants. Instead of just one, like in the previous case. So the question is, how do I obtain these independent solutions, y1 and y2? Well, one thing to keep in mind, or to remember, if we have constant coefficients, you may think about an exponential solution. The reason you may think about that is because that's what happens if you had a first order equation. So just as a matter of example here, if this were a first order ODE, let's say the y double prime was not there to begin with. So let's say this was just by prime plus cy equals 0. And just to make it easy, let's suppose b is not equal to 0. Well, I can rearrange the terms, and I can write this as y prime equals minus c over b times y. So that's just y prime equals a constant times y. Remember, again, I know that I may sound like a broken record, but remember that important ODE that I asked you to remember to memorize, namely the exponential ODE. So if you remember, we know that the solution in this case is just a constant times, well, let's just use c1 here because I used already little c, minus c over bt. So I know that the solution is in the form of an exponential. So it's not far-fetched to guess that maybe the second order ODE, the original one that I wrote here, will have also a solution in the form of an exponential. So that is the whole idea behind looking for a solution for this particular equation. So we should write it here. The main idea is to look for a solution in the form of an exponential, like e to the power rt. That r will be a constant to be determined. And of course, in the actual solution, you'll have an arbitrary constant times e to the rt. But because this is to solve a second order ODE, remember, not only we want to look for a solution in that form, but crucially, we need two of them. So we need two of them. So how can we find such a solution? Well, once you predict the format of the solution, and you're going to use this actually technique later on as well, the only way to figure out how to find it is to force this prediction, this format, into the original ODE and see if you can get the formula for r, for this e to the rt, so that it fits the whole equation. So we're going to choose y to be e to the rt, and because I need to plug this into the actual ODE, we need to take the first and the second derivative and again plug them into the ODE. So y prime with respect to t, that's r e to the rt. Y double prime is r squared e to the rt. So plug this into the actual ODE, and this becomes a times r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. So we want this to be true, basically, right? So the question is, what is r so that this is actually true, so that e to the rt is a solution? Notice we can factor e to the rt and eliminate it, and importantly, that's a consequence of linearity and homogeneity. So I can pull out e to the rt, and because there's 0 on the right hand side, we can divide by e to the rt both sides, and therefore r needs to satisfy a quadratic equation. In some sense, this is actually the easiest technique you'll see in solving a differential equation, because this is going to be your starting point, right? So to find a solution in the form of this for this equation entails to solve a quadratic equation. It's that simple. So it boils down to solving a quadratic equation that you know how to solve, right? By factorization or by the quadratic formula. But the key thing, again, we need two different r's, right? So that's why we have essentially, in the end, three cases here, depending on the possible types of roots of the quadratic equation. So either you can factor this, or if you use the quadratic formula, remember r is going to be minus b plus minus square root of b squared minus 4ac divided by 2a. You should factor it whenever possible, but otherwise always remember this formula, because especially in the complex case, it's not easy to factor. So you need to factor, use the quadratic formula whenever it's not easy to factor the quadratic here. All right, so because of the nature of these roots, we have essentially three cases. So in the first case, if the quantity under the radical is strictly positive, well, we know we have two distinct real roots. So we have two distinct real roots. R1 distinct from R2. This is basically the straightforward case, right? I mean, that if I have two different R's, that means my solution is complete. I have my two independent solutions, e to the R1t, e to the R2t. And if you look at the formula sheet, that's your first case. So once again, you solve for r, you have two different roots. That means you obtain two possibilities for this type of solutions, which is what you want. You need two independent solutions to describe the full general solution. We're going to follow up with examples right away. And in fact, actually, before we move on to the second part, let's actually throw in an example right at this moment. These cases 1, 2, 3, the second one will be a single real root, and then the complex case. All of these are given in the formula sheet, which again, I hope you have it in front of you. If you don't, you can pause, but print it out and have it in front of you. So let's write down immediately an example for this case. So suppose my ODE is y double prime minus 5y prime plus 4y equals 0. So the equation in R, which I forgot to name it actually, but this equation in R that you write down here, that's called the characteristic equation. So notice R squared goes with y double prime, R with y prime, and the constant term with y here, right? So y double prime minus 5y prime plus 4y. The characteristic equation is R squared minus 5R plus 4 equals 0. So that's the characteristic equation. This one happens to factor nicely. This factor is into R minus 1, R minus 4 equals 0. So that means you are in the case 1 when you have two distinct real roots. R1 equals 1, R2 equals 4. And so according to the formula, then the general solution of the ODE is C1 e to the R1t, that's e to the t, plus C2 e to the 4t. Now, we're going to deal with initial conditions later. Typically, you need two initial conditions here because you need to find two constants of integration. We'll go over that example in the second part. But for now, let's move on with the second part by going over the other cases, right? So there will be two more cases depending on the nature of the roots of this quadratic equation, of the characteristic equation. So we'll continue with the second part in a moment.